Okay, ladies and gentlemen, we're going to continue with section 1.5. Actually, we're starting it. This is the first video to go with this section. First thing here that you need to know, by definition, a relation is any set that's made up of ordered pairs. Any collection of ordered pairs is referred to as a relation. So you have, think of an ordered pair, for example, like 1, 7. 1 is the input, 7 is the output. Any set made up of ordered pairs is called a relation. The domain of a relation is always the set of first entries, so it's always the inputs. It's the ones that appear first in the ordered pair. The range is the set of second entries, and those are sometimes referred to as the outputs. I always like to tell my students to look at the word domain, and the very last two letters in the word domain is IN, in. Domain are the values that go in, range are the values that come out. So let's specifically look at an example. Suppose we look at the relation S, listed as the ordered pair 2, 3, -5, 6, and 7, -1. When it asks us to identify the domain of S, the domain of S is the set, that's why I put set brackets, made up of all first entries, so 2, -5, 7. Sometimes my students will ask me if the order matters, and the answer is no. You need to remember from set theory that in a set, you can list the elements in any order, so it doesn't matter what order you put them in. Next question asks us to identify the range of S, and by definition, range is the set of all second entries, i.e. the output. So we have the set brackets, and the range would be the numbers 3, 6, -1. Again, remembering order does not matter. The final question on this page, is S a finite or infinite relation, and please explain. Well, the reason S, the set that we just looked at, is called a finite relation, F-I-N-I-T-E is pronounced finite, is because you can count how many ordered pairs there are in S. 1, 2, 3. There are 3 ordered pairs, it's countable, it's finite. If I drew a whole line for you on graph paper, and of course remember a line has arrows at either end indicating it doesn't end, every place I walk on that line is actually an ordered pair, and since the line never ends, there would be infinitely many ordered pairs. So that's an example of an infinite relation. And the one that we just worked with, S, is finite. All right, the next question has to do with using graph paper to plot an ordered pair. And before we actually go to the graph paper itself, come over here to the right of this picture with me, and you will see how the quadrants are labeled. The x-axis is horizontal, the y-axis is vertical. The upper right quadrant is named quadrant 1. When we move to the left, that's quadrant 2. When we move down, that's quadrant 3. And when we move to the right, that's quadrant 4. It's almost like you're drawing the letter C. Watch my cursor. You start with quadrant 1, you trace out the letter C, and that's how you can count your quadrants. So first question. Plot the ordered pair -4, 3, and in which quadrant does this point lie? Well, -4 is an x value, so we start at the origin, which is 0, 0, and we move 4 units to the left at -4, and then we go up 3 units, -4, 3. It's kind of like playing Battleship. There's 2 coordinates, and there we have the ordered pair -4, 3, lying in quadrant number 2. Next question. Plot the origin, and then tell me in which quadrant this point lies. Well, the origin, of course, is the dot that I have on where the x-axis and the y-axis meet, because that is the ordered pair whose coordinates are 0, 0. And a very important thing to know about the origin, it does not lie in any quadrant. To be in a quadrant, a point can't touch the x-axis, nor can it touch the y-axis. So if a point is on the x-axis, or if a point is on the y-axis, then it is not in any quadrant. All right. And the next example we have here. We're given the equation y equals 5x minus 2, and we're asked, or we're being told, using this rule, i.e. equation, i.e. function, complete the following ordered pairs. The first ordered pair we have listed has -2, comma, and it's missing the back part. In other words, they've given us the x value of -2. We need to find y. So what we do is we plug it in. 5 times -2 minus 2 becomes -10 minus 2, which is -12. So that first ordered pair is the ordered pair -2, comma, -12. That is a solution of the equation. The next problem is pretty similar. We have the ordered pair 8, comma, and then we're missing the back part. Well, what that means is we've been given x, we're asked to find y. So we go to the equation y equals 5x minus 2, and we plug in an 8 for x. 5 times 8 is 40, 40 minus 2 is 38. So that ordered pair would be the ordered pair 8, comma, 38, and it is a solution of that equation. Now the next ordered pair that we're given here, or asked to complete rather, there's nothing in the front of the ordered pair, then there's a comma 7. So what we're being told here is that the y value is 7, but the x value is missing. So this time we go to the equation y equals 5x minus 2, but this time instead of putting the 7 in for x, we put it in for y. So the equation becomes 7 equals 5x minus 2. To solve an equation, we need to get the x's alone on one side, so we add 2 to both sides. That results in the equivalent equation 9 equals 5x. And to get x alone, we divide both sides by 5, thus getting the answer x equals 9/5. So the ordered pair 9/5, comma 7 is another solution to this equation. Next question. How many ordered pairs could you create using this rule, i.e., how many solutions can you find to the equation y equals 5x minus 2, and then it wants us to explain? Well, the reason the answer is infinitely many, I want you to think this through. If I gave you the equation y equals 5x minus 2 and I said to solve it, you would have to start generating ordered pairs. How many values could you put in for x? Well, I guess I would turn the question, how many numbers are there? Infinitely many. You can put as many values in for x as you want to. 1, 2, 3, 4, 5. There's one pattern all the way up to never ending. So that will tell me that there are infinitely many solutions to this equation. I've made the comment here, there are infinitely many points on a line, and the reason this connects to this problem, later on in this course, and for some of you in previous courses, if you graphed the equation y equals 5x minus 2, you'll recall that the 5 represents the slope, the -2 represents the y-intercept, that's your y equals mx plus b form. So this graph would generate a line, and how many points are on a line? Infinitely many. And each point is a solution of that equation. Okay.